this assignment, we're taking a quick look at the two parts of the fundamental theorem of calculus. We'll spend several more days making sure that we understand this visually and looking at some proofs of the idea. So we might still be at the point where you're doing this just by repetition of a pattern, but remember that we want to work towards understanding as well. So just to make sure that we're not mixing up differentiation with anti-differentiation, we have some problems going in both directions. So differentiate with respect to x is our power rule. So we reduce the exponent. And integration, we're going to do the antiderivative. So we're going to raise the exponent by 1 and then divide by that exponent. So we'll have a negative in front here. And then we add our constant of integration, since this is an indefinite integral. So we get a whole family of antiderivatives. And of course, you could write that in fraction form as well. And then we have a definite integral. So remember, the difference here is that we're finding we can interpret this as an area under the curve. So we take our antiderivative, so same as we just did a minute ago, and we evaluate it from 1 to 5. So remember, we're doing our fundamental theorem of calculus here. So we're evaluating at the upper limit, and then we're going to subtract. So maybe I should leave both signs here. We're going to subtract, and then at the lower limit, so I was going to change that to a plus sign right away. So this is our antiderivative at b minus our antiderivative at a. So our fundamental theorem here. So we're going to come up with a 4/5 as our area. So remember that in indefinite integral, we get an expression or a function as our answer. And a definite integral with constants, we will get an area. All right, here we're doing the derivative of an integral. And notice our idea here is that these two variables have to be the same. And here we're going from a constant at the bottom, so a is equal to a constant. So when we do the derivative of a constant, it will become 0. So we don't even have to think about doing the capital F of b. So when we do our derivative and then we do the antiderivative first and then the derivative, we'll get right back to this integrand, but we would have substituted the 5k squared, and it's not just a k, so we need to multiply by a chain rule, so that'll be times a 10k. So we'll come up with 10k sine of, here we're squaring, no, we've got just the k is squared, so we'll have a 10k squared there. And here we have a function that is accumulating the area under a graph, but notice the problem here is that the constant is the upper limit instead of the lower limit. So the first thing we want to do is change our accumulator function so that it has the constant as the lower limit and the variable, and you can think of that upper limit as 1/2 of x if you prefer, as our upper limit. And now you'll notice that we're looking for the derivative. So now it fits our fundamental theorem because these two are the same variable function. So all we have to do for our fundamental theorem is realize that if we integrated and then we did the derivative, h prime of x is almost going to get us right back where we started from, but we would have already substituted our 1/2 x in here, and then we would also have to do a chain rule on that 1/2 x. So our answer here will come up with a 4 times a 1/8 when we cube the 1/2, so we'll have 4 over 8 is 1/2 times 1/2 again. So I think if I did my algebra right, we'll have x cubed over 4. And now we're back to just a variety of problems here so we don't mix this up. So the derivative is the power rule, and I mixed it up right away. We bring down the exponent and reduce the exponent. And now we integrate, so we raise the exponent and divide by it. And then we add our constant of integration. And here is our definite integral, so we do the same antiderivative, and we evaluate it from -1 to 2. So we could keep, by the way, this 1/6 out in front if you wish, and do 2 to the 6th minus -1 to the 6th, and then just do the fraction once. So this would be 1/6 of 64 minus a 1. So we'll have 63 over 6, or of course divide by 3 if you wish, 21 halves, either one. All right, so just a little humor here. I'm not sure who would actually do this. Here's a tattoo of the fundamental theorem, and I don't know if that's the same person. A calculus lover for sure. Please don't do that. All right, let's continue our practice. Here we want the derivative of an integral. So notice we're differentiating with respect to y, and our lower limit is a constant. So all we need to do is remember our substitution trick. So we're going to get right back to the integrand, except we would have substituted the upper limit, and we would have multiplied by the chain rule on that 5y. So we will come up with a 5 radical 5y. We don't need to do the lower limit, remember, because it would turn into a constant, and then the derivative of a constant would be 0. All right, so here our upper glob is still in terms of the variable x, so we only need to remember to put that when we differentiate in this function. So the derivative of this integral gets us almost back to the integrand, but the important idea here is remember the chain rule. So I can't read what I just covered up. Is that a minus 5x? And then our chain rule, so do not forget. So you could put this chain rule out in front right away. So you don't have to make these into two-step problems here. If you want to put your chain rule in front, that would be fine to do that in one step. All right, derivative of cosine, negative sine of x. Cosine is the derivative of sine of x. So we always have to be careful to reverse our thinking to go to antiderivative. And then let's evaluate. So the antiderivative was sine of x, evaluating from 0 to pi over 3. So we want to do the sine of pi over 3 minus the sine of 0. And the sine of pi over 3, that's our tall 30, 60, 90 triangle. So square root of 3 over 2, and the sine of 0, of course, on the unit circle is 0. So square root, oops, not mess up that radical there. Square root of 3 in the numerator over 2. All right, the derivative of secant squared requires a power rule first, and then a chain rule on the secant. So again, if you've done these several times, you can feel free to go right to the answer. If not, be careful not to miss the chain rules. And here, antiderivative, we're saying secant squared is the derivative of what? It is already the derivative of tangent of x plus a constant of integration. So here, when we evaluate, we'll have tangent of x evaluated from pi over 4 to pi over 3. So the tangent of pi over 3 minus the tangent of pi over 4. So I hope you've got this now. The tangent of a tall triangle, this would be square root of 3 over 2 divided by 1/2. So it is square root of 3. And the tangent of pi over 4, of course, is our 45 triangle, which is 1. So square root of 3 minus 1 would work. Here we're doing the derivative of an integral. So again, check to make sure we're doing the derivative here with respect to p. And we've got a constant as our lower limit. So we need to take our 8p squared and put it into our integrand. So you can, again, simplify that right away. But remember, it's not just a p, it's 8p squared, so it has to have a chain rule. So 16p out in front. And here we would have a 72p squared plus 3. So our fundamental theorem. And here we have an area accumulator function. G of x is accumulating the area under the log of t plus 2, and we're evaluating from a constant to a variable in terms of x. So when we do the derivative, we will be right back where we came from. We'll be right back to the natural log function, but we will have evaluated at 1/7 of x. And 1/7 of x has a chain rule of 1/7. So whichever way you want to write this does not matter. You could get a common denominator in here, but you don't have to, so I think that answer would be fine. The derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x. So we evaluate e to the x from 0 to 3 for our definite integral. So we'll have e to the third minus e to the 0. And of course that would be a 1. E to the 0 is 1. The derivative of 1 over x, think of this as x to the negative 1 if you prefer. So we do our power rule for our derivative. And here the antiderivative 1 over x is the derivative of the natural log. Here x could be either positive or negative, so we want to put absolute value there. Plus c. And 1 over x is the derivative of natural log. And now you might say, well, what about the absolute value? Well, it doesn't matter here because we're plugging in positive numbers only. So we'll have the natural log of e minus the natural log of 1. The natural log of e is 1, and the natural log of 1 is 0. So we'll come up with 1. All right, 13 we're differentiating with respect to m. When we differentiate this integral, we're going to get right back almost to the integrand, except we will have replaced our variable with our upper limit. And then there would be a chain rule on that upper limit. So the derivative of ln of m is 1 over m. And here, let's evaluate. Hopefully you recognize that this term is just m. If you're not sure about that, rewrite it. Those are inverses. Change it back to an exponential form. And here we'll come up with a 1. All right, and g of x is equal to the integral from 0 to 3x. So what happens if we're looking for the derivative? The derivative is going to undo the integral, except that we would have already put this upper limit into our integrand. So we want to put the 3x into the s values, both of them. So we would have plugged this in. And then the second part at 0 would be a constant, so that derivative would turn into 0. So here we'll have 45x squared minus sine of 3x, if my algebra is correct. And I think that looks like we're done. Thank you, guys.